Till he's finished.
Part 3, materials.
Material.
Physics.
Material goods.
The art of materials, not textiles, the art of cushion making.
Oh. I like cushions.
I do quite like some cushions. Density. What is density, Mr. Connor Durkin? Mr. Connor Durkin, thank you.
It's when you're really, really, really stupid.
The density of a substance is defined as its mass per unit of volume, which gives a clue to what the equation is going to be.
It's mass over volume.
Yes. The unit is just... That's a lot of arrows there. The unit is just a kilogram per cubic metre.
So you have to make sure you convert all the units into meters cubed and...
and that's it for density. It's just the mass in relation to the size of the object, really. Hooke's. But now onto Hooke's law, not to be confused with Peter Pan's. States that
the force needed, to stretch a spring is directly proportional to the extension of the spring from its natural length.
So, in other words, F equals K multiplied by the change in length.
K is a constant.
So, if K is big, then the spring is quite stiff.
Oh.
You can find K by plotting F against the change in length because K will be the gradients.
Indeed.
Yes.
Y equals mx plus c, win.
Yeah, though a spring is stretched beyond its elastic limit, it will not regain its initial length when the force applied is removed.
Very quickly, side note with springs, little springy buggers. If they're in parallel, the extension of each spring will be the same, so you have to add the forces needed to stretch the springs, because if you like, they are the same type of spring. Because if they are the same type of spring, you have to pull twice as hard to move them both the same amount. But if they're in series, as in, like the diagram says, then force is a sum of their reciprocal. Ooh, that's fancy. The picture makes it much simpler than it sounds. Just think that as you pull one spring, the second gets pulled, so it makes sense under some level.
So as you pull one, it already extends the next one a little bit without you putting in any more weight. So it's the same if you've done unit 1, which you must do, otherwise you're not going to do very well in unit 2. It's the same as resistance, but the opposite way round. In the way that do you remember resistance?
No,
1 over R.
I tend to forget all horrible
1 over the force. Yeah, the force is okay.
Okay,
get that.
Yeah.
Right.
Let's just move on. We're so good.
Yes. Okay. That was a long side note, but also the area underneath the line in the graph we had earlier is the elastic potential energy, which you will know from our last video is the stored energy.
Is it?
This is given as half F times change in length, but that is just the area of the triangle rearranged.
Half base times height.
Yeah, I know. Sneaky.
Stealthy.
Ooh. Tensile stress, strain, and Young's modulus.
Oh, God.
The elasticity of a material is its ability to regain its shape after it's been deformed. Interestingly, deformation that stretches an object is tensile, and the deformation which compresses an object is compressive. That's very interesting.
The tensile stress is the force, tension, per cross-sectional area.
Measured in pascals
or newtons per metre squared.
The tensile strain is the change in length or the extension divided by the length.
And this is a ratio, so there are no units. One of the very few ones where there are no units whatsoever.
Linked to this is the Young's modulus, which is simply the stress divided by the strain, again measured in pascals.
Or newtons per metre squared. Yeah, okay.
Here is a rather lovely example graph, which tells you all of your keywords. Firstly,
the limit of proportionality. P.
Yay! Where Hooke's law no longer applies. The end of the straight line.
The end. Then the elastic limit, E, after which point the material suffers plastic deformation. It cannot go back.
Yeah, up till E, it can still go back to the origin in the graph, but it doesn't obey Hooke's law completely. But at E, it then will have a permanent extension, which is what you just said. Then the UTS, or ultimate tensile stress.
Tensile stress.
After which the material loses its strength. The highest bit of the graph.
This part is sometimes called the breaking point or breaking stress point.
No, it isn't. It's called the breaking stress. Because
point.
B is where the material breaks.
The breaking point. That's what it said.
No, but UTS is some kind of called breaking stress. See, educating you and Mr. Connor Durkin at the same time. Now, for some other nasty words, which you arguably have to do with physics, the stiffness of a material can be compared using the gradient of the stress-strain graph, equal to the Young's modulus.
Indeed. The strength of the material is the ultimate tensile strength.
Yeah.
Strength?
Yes, stress. Same. It's the same thing. We just had this conversation. A brittle material snaps without any noticeable yield or dip after the elastic limit.
A ductile material can be drawn into a wire, shown by a longer line in most cases.
The last part that never comes up is loading and unloading.
Your weapon. A metal will return to its original shape unless it has passed the elastic limit, whereas a rubber material will return back to its original shape, but it has a much lower limit of proportionality. The area simply tells you the work done.
Yes, between the two. So, in this case, up till P, if they let go... Yeah, that's the return journey, if you like.
Stripey.
But if it went any further, there would be an extension. You could draw a pretty line.
The colours are hurting my eyes.
The colours are hurting my eyes as well, actually. But that's it for materials, Mr. Connor Durkin.
That's the end?
That's it.
I'm
It's really short.
I'm not
That was really short. We could fit this into an hour. An hour.
Really?
Will and Connor's amazing physics revision unit.
Seductive whisper.
I love my seductive whispers, as does everyone. Including your mother, Connor. Thank you for listening. Goodbye.
My dad listens to these, you know. Hi, Dad.
Hey, Connor's dad.
Oh?